percent reaction, and we're going to couple this with percent yield. Now, what is percent reaction? Well, percent reaction, it is just the yield in percentage of the products being formed. Now, before I get into the nitty-gritty here, I just kind of want to separate this into two aspects. Okay, so right now this here on the left side, we'll talk about the percent reaction. Okay, and then here on the other side, we'll do it as KEQ, because I want to kind of outline the similarities and differences between the two. Okay, so let's start with KEQ, because this is what you should be familiar with, that we've been working on for the previous few videos. For KEQ, what is it? If you remember, it is the relationship of the ratio between the concentration of the products and the reactants. Okay, so the relationship of the ratio, okay, between, I'll just put B/T, okay, for between, okay, it's the ratio between the concentration, okay, of the product. I'll just put it for prod, okay, so the ratio between the products concentration and the concentration of the reactants. Now, it's also important for us to remember that KEQ, what is it determined by? Okay, the KEQ, remember, the effect of KEQ, it's only determined by temperature. Okay, I'll just put temp for temperature, okay? It is only determined by temperature. Now, obviously, for percent reaction, it is not only determined by temperature. I'll write this here. It is determined by this concentration, okay, of the products and the reactants, and temperature as well. Now, what is this percent reaction? Okay, well, I'm going to outline it as a formula down here, but for now, just in words, percent reaction, like I said, it is the percent yield of the products. Okay, percent yield of the products, because we eventually, in our practice problems later on in this video, we want to test how much this concentration of the products have been made or have been yielded compared to how much it can maximally produce. So maybe I'll write this here. Compared to how much can maximally, I'll just put it max for short, to maximally, to how much can maximally be produced. In case you're a little confused, let's bring this down here to an actual formula. And it's a very, very obvious formula. Our percent yield is just equal to our actual yield, so how much we actually got, over what we are theoretically, okay, so I'll just put theo for short, theoretically yield, all multiplied by 100% after you divide them. Okay, so it's kind of like a grade that you get. You're theoretically supposed to get 100% if you study, and what you actually get, though, is most of the time a lot less than that. So this is your actual grade that you got correct. This is what you were supposed to get. You divide them, multiply by 100%. That is your actual grade of, the paper that you submitted, or the test that you completed. Okay, that is the percent yield. It's that simple. Okay, it's how much you actually got, or how much in scientific in chemical reactions, how much you actually got to how much you should have gotten, or theoretically should have gotten. Now I'm going to continue this little dichotomy between the two here with a line here, and outline a few conditions. Okay, so for KEQ, it's important for us to understand here that if KEQ, hopefully you remember this, if it was greater than 1, what is being favored? Was it the products? Was it the reactants? Take a minute to think about it. If you need to pause the video, think about it, right? What do you think would be favored. You should have gotten products being favored. Now hopefully this should have been a little bit obvious, because remember our K, okay, when it's at a temporary equilibrium before it becomes KQ, remember that the formula was the products on the top and the reactants on the bottom. Of course, if this value is going to be large, it would have to mean that the numerator here has to be larger than the denominator. Okay, so this one has to be larger. And if the products are always on the top in the numerator, of course, that means this number would be bigger. Okay, so and if it's greater than 1, of course the products are favored, because this here would be a lot larger of a number present than the denominator on the bottom. Okay, so that's a way to think about that. So if KQ was then less than 1, what would happen? It would be the opposite. The reactants are favored, because obviously the denominator would be larger. And lastly, if K, okay, is equal to 1, or maybe we can put approximately, okay, equal to 1, doesn't matter. Okay, if KQ is equal to 1, the concentrations, okay, of the products and the concentration of the reactants are the same, or pretty much the same. That is for K. Now let's have a look at the percent reaction aspect. Okay, the percent reaction, again, have to know these. If the percent reaction, let's go to the lowest number between a scale of 0 to 100%. Okay, obviously we have 1%, which is approaching 0. It's a very, very small number. Okay, that is not a decimal. So if percent reaction is going to be less than 1%, so it's very, very small, approaching 0, there's actually no reaction. And in contrast, if the percent reaction is going on the extreme high end, so if it's greater than 99%, then it would be the opposite. It's pretty much complete. It hits completion. And when I say completion, I just mean that the reverse reaction is negligible. Of course, there's always going to be this tug-of-war dynamic equilibrium, right? If you have no idea what this dynamic equilibrium means, look at the video link in the description below, where I go into this, which is a prerequisite to this video. So it hits completion. Of course, there's always going to be some tug-of-war, but we're just going to assume that this reverse reaction, okay, rev for reverse reaction, is negligible. So that means there are two other conditions that we're going to have to put down here. If the percent reaction is less than 50%, what do you think would happen? The reactants would be favored, kind of similar to this one here, okay? K being less than 1 for the percent reaction. If it is less than 50%, the reactants are favored. And of course, if the percent reaction is going to be greater than 50%, it's the opposite, similar to this one. K being greater than 1, the products are favored. Let's have a look at a few practice problems. As we write this down, of course, it's probably wise to write down the chemical equation for this. So we got NOCl, gaseous state, reversible reaction, because obviously we're talking about equilibrium as the focus, and then we have NO, our gas, and Cl2, gas. Now it says 1 mole per liter, 1 mole over 2 liters was placed, and then it got heated until equilibrium. So it seems that we got to create an ice table, because we have something initially, and then look at the very end. It says at 400 degrees, okay, this much percent, okay, was obtained. Okay, that we got yielded. So it seems like we got to use an ice table, because ice obviously is initial, and then some change is going to happen, and then we get E for equilibrium. Okay, so obviously at the end it's asking for what would be the equilibrium concentration at the very end. So it's quite obvious that we need to create an ice table. So let's draw an ice table here. ICE. And let's put our NOCl. Let's put our NO and our Cl2. So we'll first tackle our I's over here. So for I, initially, what do we end up getting? Again, just always use a disclaimer that this is all going to be in concentration. So for NOCl, we had 1 mole over 2 liters. We all know that this is going to be our formula for concentration. So it's N over V. So we have moles, our 1 mole over here, and we have 2 liters over here. So 1 divided by 2 gives us 0.5, okay, moles per liter. So that is for NOCl. How about for NO? Well, we have none produced because at an initial, none of them are being produced yet. This got to decompose to make that. Okay, so that's going to happen a little bit later in this reaction. So right now we just have 0 and 0 for both of the products. Let's continue to go with a change. So for our change, do we have to put our negatives and positives? Absolutely. This here is being consumed, so of course we're losing it, so that's why there's a negative value. These are being gained, so we got to put them as a positive value. Now x is going to be our variable here. However, we also have to understand that this needs to be balanced. Okay, so pause the video, balance it yourself quickly. 2 here and 2 here. This means that we got to put a coefficient in front of the variable of x. We have negative 2x. For here it would be plus 2x, and here would just be 1x because there's only one coefficient. Now let's put them together. 0.5 minus 2x, 2x, and x. What are we going to be doing now? Well, it says at 400 degrees, the percent yield of Cl2 was 56%. Okay, so this one over here, we're going to concentrate on this guy. Well, what are we theoretically supposed to be getting? Okay, only 56% was actually obtained, but we're supposed to be getting a theoretical amount. What would that be? Well, we had NOCl here at 0.5. You know what, let's get rid of the units for now, just to make it simple. Okay, so we got 0.5 initially of NOCl, and this NOCl is going to be creating these products. Okay, well, for this to create this Cl2, we have to look at our coefficients, because right now we have coefficient of 2. All of a sudden, when it breaks up into Cl2, there's only a coefficient of 1. This is very important. So what you can do is, okay, you know what, I'm going to put moles per liter here actually, but I'm just want to highlight and label that this is because it is NOCl. It's important to do this. So remember, with my rule, whenever you multiply by a fraction, it's because this is the first thing to do whenever you're confused of how to convert, using stoichiometry, so that they all cancel out appropriately. Well, if we want to convert this NOCl to Cl2, well, whenever we have this, we also obviously want Cl2. So does Cl2 have to be on the bottom here, or does Cl2 have to be on the top over there? Of course, Cl2 has to be on the top over here, because that's what we want at the very, very end. We're looking at the percent yield of Cl2. Okay, we're revolving around that. We don't care about NOCl anymore. So our NOCl has to be on the bottom here. Okay, and we want these to cancel out appropriately, so we're just left with this. Well, for our NOCl, we're supposed to be getting 2, so I'm just going to be putting 2 moles. Okay, for our Cl2, okay, I'm sorry, moles per liter, 2 moles per liter. Okay, but for our Cl2, what is it supposed to be? Just 1, so I'm just going to be putting 1 mole per liter over here. So technically this is all over 1. Okay, so you can technically multiply these fractions, because it's moles per liter. Okay, of NOCl cancels out with this moles per liter of NOCl. So what do we end up getting? We're just ending up getting 0.5 times 1 divided by 2. Okay, so what is that? That's obviously 0.25. Okay, so 0.25, that'll be moles per liter of the Cl2. This is what we're theoretically supposed to be getting. I'll just put here, this is what we're theoretically supposed to be yielding. Okay, that means if I were to write it out over here, let's get our theoretical yield formula, sorry, our percent yield formula, or percent yield, and our actual we don't know, and our theoretical we do know. Okay, what are we going to be getting for actual yield? Okay, we can put actual if you want. You can write actual, okay, but I'm just going to put a question mark. For percent yield, do we know? Well, we absolutely do. The percent yield was supposed to be 56%. So I'm actually going to just change this here to be 56%. Okay, and then of course we have to multiply this all by 100%, or in case you're confused of how I did that, obviously this is 50%. You always have to multiply by 100% in order to do your percentages. Well, obviously this is times 100%. If you divide this all by 100%, you got to divide the left side also by 100%, and then you end up just getting this as 0.56. Okay, so that's how I got the 0.56. And then we just diagonally cross it over, or if you want to think about it another way, this here we're going to have to make sure that it's on its own, isolated. So right now it's dividing by 0.25. I want it to be alone. So how do I get rid of this divided 0.25? Just do the opposite. It is multiply 0.25. So they cancel out. If I do it on the right side, I got to do it on the left side. There we have it. So then our question mark ends up becoming 0.14. Okay. So this is what we're supposed to be getting, 0.14 moles per liter. So this here is going to be our X value, okay? So this here would be 0.14. Now, for our NO, we just got to do 2 multiplied by this X value of 0.14. What do you end up getting? And we're getting 0.28, okay? So this here will be 0.28. This one here, like I said, was 0.14. And then how about this one over here? You end up getting 0.22. And of course, all of these are in moles per liter. If you want to write that at the very end, like this, it's up to you. Okay, so this is the answer. High temperatures, carbon dioxide decompose into carbon monoxide. And luckily, we've already had it written out here, which is nice. At equilibrium, oh, this is definitely, we have to use an ice table, okay, because we have something happening initially, as written over here. Initial was 1.5 moles per liter, and then at equilibrium, we only ended up getting this. It's quite obvious we got to use an ice table. Let's start with our reactant over here, our CO2, and then our CO, and then our O2. So initially, what do we end up having? Well, we don't know what it was for CO2. Oh, never mind, no, CO2, it is given to us. Okay, initially it was at 1.5 moles per liter. It's already in concentration. Again, all of this will be disclaimed as concentration. So we have 1.5, which is nice. And then we don't know what our products are going to end up, okay? Eventually they will, but right now it's just at 0. And then our change, of course, we've got to be putting a negative value. This is being consumed, this is being gained, so this is a positive, this is also being gained. And then we're going to be putting 2x because that's our coefficient. 2x, also another coefficient of 2, and then just 1x coefficient of 1. And then we just do 1.5 minus 2x over here. You just sum them up, 2x, and then x. Okay, at equilibrium, O2, so we're going to be revolving around here, okay, at equilibrium. This one is going to be at 0.15 moles per liter. Okay, this is all still moles per liter. Determine the percent reaction. Okay, we know that our percent reaction formula is going to be our actual yield over our theoretical yield multiplied by 100%. Okay, if the initial concentration was 1.5, okay, so that's what we have here. What is it supposed to be? Okay, well, we have 1.5 moles per liter of what? Of our CO2. And we don't want that, right? What did I say? We're revolving around what we have at equilibrium, which is O2. So our O2, is it going to be up here or is it going to be on the bottom here? Of course, it has to be on the top here because that's what we want. Okay, we want our CO2 to be down here so that they can cancel out appropriately. So let's have it written out. Our CO2, okay, or this one over here, what is its coefficient? It's a 2, so we're going to have to be putting 2 moles per liter. For our O2, we don't know, no, we have it. We have it 1 mole per liter. Okay, I'll put this technically all over 1, and then you just cancel this out, cancel this out, cancel this out. So then we're just left with this one. Okay, so this will just be 1.5 times a half. What would that give us? It gives us a 0.75, okay, moles per liter of oxygen. Okay, if this is the case for our oxygen, this is what we are supposed to theoretically get over here. So I'm just going to bring this down over here so that our percent yield can equal over 0.75. Our actual is actually 0.15, all multiplied by 100%. What do you end up getting? I end up getting 20%. That's the answer. When ammonia is heated, thankfully we've already gotten it, okay, given to us. The amount of ammonia initially, decomposes into N2 and H2. Initially it was at 8 moles per liter, okay? And again, thankfully it's just 1 liter, so that makes it easy. So we have a concentration of 8 moles per liter, and then it eventually drops to 6 moles per liter, okay? So, and does not change after that with further heating. What is the percent of hydrogen gas being made? Of course, right now we're highlighting and revolving around ammonia, but we have to shift our focus towards hydrogen gas. Now, put a nice table. Let's put our reactants, NH3, our H2, and our N2. Like I said, this here is all going to be in moles per liter. So here would be 8, okay, divided by 1 liter, so we 8 moles per liter. For H2, we have no idea, and then N2, we have no idea at the very beginning. And then we have to be putting our changes, negative 2x, 3x, and an x. Sum them up, there we have it. The amount of ammonia, like we said in the question, it drops to 6 moles, okay? So this means if there's no more change with further heating, this is obviously at equilibrium, okay? That means we can actually kind of change this into 6, okay? So we can actually just sum them up so that this becomes 8 minus 2x is equal to 6. So if you just want to do it up here really quick, okay, 8 minus 2 gives you 6, that's negative 2x, negative 2, obviously this is just going to give you 1, okay? Now, we can actually just put this x as being 1 over here, okay? So this ends up becoming 1. And then we just put our 1 over there as well, so that 3 times 1 gives you 3, okay? So we can actually be putting this as 3 and be putting this as 1. Now we have to, what do we say? We have to make our shift of focus go towards the hydrogen gas. We've done it over here. Okay, so this is where we're supposed to be putting our focus right now. Let's write down our percentage yield, because that's what the question is asking for. And we have to be putting our actual on top, and then our theoretical on the bottom, all multiplied by 100%. Okay, what are we actually getting? Well, unfortunately, we actually got 3. Okay, what are we theoretically supposed to be getting? Let's shift our focus. This is our NH3. It has 8 moles per liter of concentration. We're, again, using stoichiometry going towards the H2. We have to be focusing over here. Well, let's put it here on the side. For our 8 moles per liter of NH3, I do not want that anymore, so again, first line of defense, multiply by a fraction, okay, if you have no idea what to do. And then, of course, we have to get rid of our moles per liter of NH3 because obviously we're looking for the percentage of hydrogen gas. So obviously our H2, is it going to be on the bottom or is it going to be on the top? Of course, it has to be on the top, okay? So I'll just put moles per liter of H2, okay? And on the top, so then our moles per liter of our NH3 is going to be on the bottom. Well, what is our coefficients? Well, for our NH3, right over here, it is a 2, so we're going to be putting 2 moles per liter. How about for H2? It's a 3. We're going to be putting a 3 over there. So this moles of NH3, moles per liter of NH3, cancels out with this moles of liters of NH3. So we're just going to be ending up getting 8 times 3 moles per liter of H2 divided by 2. So what do you end up getting for that? I end up getting 12 moles per liter of H2. So this is our theoretical. We should be getting that. Unfortunately, we only got 3. All you need to do now, 3 divided by 12 times 100%, obviously that's going to give you 25%. This would be the answer. Okay, these are the 2 green questions of the day. This is the first one, and obviously this here is the second one. Please give this a try on your own, pause the video, work on it on yourself, and I'll be giving you the answers shortly. Here's the answer to the first question. This is the answer to the second question.